today something to do with Professor Alexei Stravinsky. I met him 20 years ago in Taiwan at International Conference on Gravitation. He gave a talk, beautiful talk, on his classic inflation scenario, R-square inflation model. Then at the time, that was not most popular, just one of the model, but I was curious about the origin of R-square term, just because I'm working on conventional geo, Einstein gravity, not any modified theory. So I tried to understand the origin of that, and I chatted many times with Alexei, just because after that one, 20 years ago, I met him a couple of times in Taiwan, in Japan, in Russia. So today I'm going to explain about the origin, one origin, not the origin, just an origin of R-square term, or even higher curvature term. That is the effect fraction inducitor. This means that whenever we have quantum field inducitor, it is more natural to have higher curvature terms. So I'm going to explain about that today. Okay, yep. The last time I met Alexei, that was last summer, last June, at JLW meeting. So you see a photo, Alexei was giving a talk. That is something to do with the particle creation in expanding universe. That is one of the topic I pursued in 80s and early 90s. So somehow overlapping the common interest. Right-hand side, Remo Lupini is giving a talk. Now, this is data from Planck 2018. Actually, this is a summary of inflation models. Then here, R-square, the Stravinsky inflation model is so far the most viable model in this diagram. There are many models such as the chaotic inflation model and other models, but so this is quite consistent with Planck data. Now, what is the origin of this term? About that, then R-square inflation model or R2 inflation model by Stravinsky. On the other hand, the origin, it is well known in quantum field theory that any quantum fluctuation of matter field or space-time itself, perturbation, then always we have higher order curvature terms. Then almost 20 years ago, Professor Longjun Kai, the president of BRICS, now he's the president of Ningbo University, so quite busy. We just proposed another concept, entirely different. That is based on quantum theory, just because Friedman equation equivalent to the black hole thermodynamic law, first law. So this means that there must be a connection between expanding universe, FRW type, expanding universe, and also the black hole entropy. So the Ted Jacobson of Maryland University, he personally suggests that our paper actually claimed, but we never claimed, but actually our paper argued that the lambda is nothing but entanglement entropy. That is a quantum concept, but longer, and I have never published any paper claiming this story, but this is interesting concept to explain about the inflation model. Now, let me explain about how to compute, how to find the effect fraction. I'm not talking about perturbation theory. I'll talk about the exact one-loop effect fraction that is based on the quantum field theoretical method concept, first proposed by Julian Schwinger, then his former student, Bryce Dewitt, elaborate that formalism. Now it is called in-out formalism. According to that, then there is a very classical textbook, two-volume book, Global Approaches to Quantum Field Theory. Now, the one-loop effect fraction is nothing but the scattering matrix, scattering amplitude between in vacuum and out vacuum. So once we have the knowledge or information about in vacuum and out vacuum for quantum field, then in principle, we can compute this exact one-loop effect fraction. So that is the concept behind. Now, one of the interesting features of this in-out formalism is that whenever there are some particle production, spontaneous particle production, for instance, from black hole or expanding universe, according to Lenny Parker, then there is a consistency relation between the amplitude square and the imaginary part of the one-loop effect fraction. This is a mathematical consistency, not just concept. It should mathematical identity following from this scattering matrix in our formalism. Now the concept, actually, in the language of Feynman diagram, that is something like a quantum field interacting with background space-time, or gauge fields such as photons, or the non-abelian the gauge field. Then summing up, all this is equivalent to this scattering matrix. That is the concept. So very powerful. Now question is how to realize, how to make it for concrete computation, for concrete application. That is a question. Now in our formalism, as I explained, as I said, we define, we choose in vacuum and out vacuum for quantum field in two different regions to separate the space or time region, then always Bogoliubov transformation between them. I'm talking about linear theory, linear quantum field theory. Then we have the operator, creation, annihilation operator for particle and creation operator for antiparticle. This is the Bogoliubov relation between two unitary inequivalent Fock spaces. Now, using that knowledge, then the out vacuum is superposition of multi-particle entangled state of in vacuum for bosons, for scalar particles. And for fermions, we have Pauli blocking principle applying here. So only one pair of fermions can be produced. And here, beta square, that is the mean number of spontaneous produced particle. Now, question is how to find exact one-loop effect fraction out of that the concept. That with my Korean two collaborator, Hyun-Gyu Lee and Yong-Sung Yoon, we realized that actually the integrated one-loop effect fraction is nothing but log of Bogoliubov coefficient, so-called the vacuum persistency amplitudes. So this is still symbolic. Now question is how to find, how to derive something well known, the expression for one-way impact reaction. For instance, Heisenberg-Euler type in strong field QED. That is our the challenge at that time. At the time that all the 20 until 2010, and this formulation also allowed to find finite temperature exact one-way impact reaction in the same formulation. This is based on the actual computation is based on the concept of finite temperature field theories from a vacuum in doubled Hilbert space. Now that we found this concept in terms of the complex analysis, actually one-way impact reaction is given by this expression for finite temperature. Just take zero temperature limit for zero temperature impact reaction. Just because this formalism, in our formalism, assume will also just consider the case of spontaneous particle productions. So the imaginary part of this impact reaction is given by the Vogel-Bob coefficient and also Bose-Einstein or Fermi-Dirac distribution for given initial time or initial distribution. Actually, this formulation just evolved according to our formalism to future time or another space infinity. Then consistent pair production rate, actually that is given by this formula, but I will not explain the technical detail of this. You may look at those papers. Now, this is the real and the genuine our contribution, that is gamma function regularization. We observed that the Vogel-Bob coefficient known in quantum field theory in strong field regime that has this expression, the fraction of gamma function, alpha and beta. Now, log of gamma, that has this integral representation. We realize that that is nothing but the famous Schwinger-Propertine integral. So, using that, just because of the complex analysis, we could fully make use of the beauty of complex analysis, such as the Cauchy theorem, Cauchy-Legendre theorem. It turns out that the one-way impact reaction, whenever there is spontaneous particle production occurring, then it has something to do with imaginary part. That can be explained in this gamma function regularization as Cauchy residue. So mathematically consistent and very straightforward. Once you know the gamma Vogel-Bob coefficient expressed as a rational function of gamma. That's it. Now I'll persuade you through a couple of examples in strong electric field, then Vogel-Bob coefficient by solving Klein-Gordon equation or Dirac equation in constant electric field. We know that in constant electric field produce electron-positive pair or particle and antiparticle pair. That is known as Schwinger pair production. So for them, then applying the one-way impact reaction, just apply gamma function regularization that we end up with this formula for scalar field or spinor field in strong electric field. Actually, the real part, that is nothing but the famous Heisenberg-Euler and Schwinger one-way impact reaction in constant electric field. On the other hand, as I emphasized, it has imaginary part that comes from the simple pole of Cauchy-Residue from Cauchy-Residue theorem. That is very consistent. So this population is very powerful. Now I'll explain how to apply these two, de Sitter space, and why we have high-order curvature terms in de Sitter. De Sitter is something like lambda CDM cosmological model without matter, just lambda cosmology. Now in de Sitter, actually for global coordinate or geometry, then gamma Bogoliubov coefficient alpha and beta is given by this term. Now just apply the formulation and combine together with gamma function regularization. Then this is one impact fraction here. D, that is density of state, just because we are counting the impact fraction per volume, per space-time volume. So that density of state has this expression and the mean number, and this work for any space-time dimension. Now, just skip all this formulation, just explain about the physical origin. Just one origin of high curvature terms. Just expand this four-dimensional exact one of impact fraction in terms curvature. Then you end up with one of impact fraction r square term times the higher curvature terms. The lowest term is nothing but r square term. So this r square term modify Einstein-Hilbert action, that is R over G. So that is the origin. This implies that in de Sitter, whenever you have a quantum field or any classical field, then always the consistent framework is including higher curvature terms, but higher curvature term is always small than the lower curvature term. So the leading term is Einstein-Hilbert term, the next leading term is R square term. So this is what I just talked to Alexei, and he wondered about just because that quantum effect must be small, but this is true. That explained. Yep. Now let me briefly explain about how to extend to Einstein-Maxwell theory in de Sitter or anti-de Sitter. Then QED means that by QED in two-dimensional de Sitter, we do not have a magnetic field just because magnetic field exists more than three space-time dimension, not in two, one time dimension and one space dimension. So that is the reason. Now it has many applications. One is a charged black hole. So it explains about when Hawking radiation stops emitting the Hawking radiation, so-called Hawking radiation, for extreme limit. But we have electric field on horizon. This electric field produce particle and anti-particle pair, so that means that charged black hole emit the charges. So charged black hole, extreme limit of charged black hole still discharges, and it evolved to something else. So for the one interesting feature of this near extreme or extreme black hole is that when you look at close to the horizon, it looks like A-2 cross S2 for four-dimensional charged black hole. Or for regular, the non-extremal black hole, then Lindlar, two-dimensional Lindlar space times S2. So the quantum field theory near the horizon, just because Hawking radiation or shingle pack production dominantly occur just near the horizon of black hole, charged black hole 1-up. Then just solve quantum field theory in this the near horizon geometry to find the formula for rotating black hole inducitor. Actually, that is a S wave, scalar wave, and that is equivalent to two-dimensional QED inducitor. And Longan and I just introduce new concept just because Hawking temperature is the Bose-Einstein or Fermi-Dirac with Hawking temperature. Now we have a similar effective temperature concept. Then Longan and I just realized that in two-dimensional de Sitter or anti-de Sitter, we have effective temperature for charge emission, Schwinger formula. That is given by the acceleration of charges, the unknown temperature, geometric, the means of unknown temperature square or given Hawking temperature for de Sitter, and for anti-de Sitter. Actually, anti-de Sitter always just bind pairs, so hard to make it pair production suppressed. So we have negative contribution for effective temperature. So physically makes sense. Now for one node, I'll skip that. Now in terms of effective temperature, why do we have this effective temperature? Just because Narenhof, Peter, Furling, and Dessler Levin, they just figure out what would be the unknown temperature in de Sitter or anti-de Sitter, accelerating observer, what temperature he or she would have. They found out very interesting formula, very simple one, the unknown temperature square plus given Hawking temperature for de Sitter case, but actually it becomes two-dimensional anti-de Sitter divided by some numbers. So for anti-de Sitter, we have a negative sign. Anyway, this effective temperature determines the dominant leading term for the unknown effect. Now, the effect temperature for Schwinger formula in ADS2 or DS2, we found out, as I explained, is given by this effective temperature for de Sitter and anti-de Sitter. Leading term is nothing but Boltzmann factor, the effective mass in de Sitter or anti-de Sitter, then divided by this effective temperature. That is what Longan and I found. Now we can further elaborate and find the one-loop effective action in this space. Then this is the one-loop effective action for de Sitter, anti-de Sitter. Then expand this proper time integral, just expand as a power of S. Then all this exact one-loop effective action is combination of the Maxwell scalar and the scalar curvature. So we expect very strong coupling between Maxwell's field and the curvature terms for Einstein-Maxwell theory. Now, technical details, so I'll skip most of technical thing. Now, let me explain about the physical concept and what can we understand in the future, where to apply this one-loop effective action. Then, as I explained, that it recover the famous Heisenberg-Euler and Schwinger-QED one-loop effective action in constant electric and magnetic field. we discovered that after few lines of computation, actually, the original paper by Heisenberg-Euler and Schwinger, tens of pages of computation, but they apply conventional field theoretical computation to find one node. But here, by applying Schwinger, do it in our formulation, combined with gamma function regularization, I show you that actually only few lines of computation will give you exact one node effect fraction. Now, then I apply that to the theta space and explain about the origin of high curvature terms, why we have all higher curvature terms. And one of the effect fraction in de Sitter and anti-de Sitter, then with my collaborator, we are working on high dimensional, the case one of effect fraction in de Sitter or anti-de Sitter. Then actually, when we have this one of effect fraction, then you recover not only Minkowski space-time results limit, but also the without the electromagnetic field the case too. I have 5 minutes for including Q&A. What? Oh, for everything. Oh, no, just let me explain. The last line, all right, yeah. QED phenomena in de Sitter, anti-de Sitter, it can apply to cosmology just because when you compute the polarization effect in cosmology, the CMB effect of higher the polarization, the higher QED effect, then you need this formulation. Though actually that this polarization effect will be highly suppressed because of strength. The electromagnetic field strength is so small. So, however, actually for cosmic scale, when the probing photon propagate cosmic distance, then there will be measurable amount of this, the one effect. And also I explained that the effect temperature. Temperature is very useful and physically intuitive concept to explain about the particle production, spontaneous particle production in non-perturbative quantum field theory. For instance, Hawking radiation. Hawking radiation can be explained along this line that the effect temperature is nothing but the Hawking temperature, just because for the uncharged black hole, in the complex analysis, there's only single pole from the event horizon. So by summing up all the loops, then actually recover the Hawking temperature. Now, the emission from near extremal charged black hole, that is very interesting just because we do not understand the complete evolution history of charged black hole via Hawking radiation and or Schwinger emission of charges, that is discharge process. How charged black hole evolve due to this emission, that can be explained only this framework. And also it explain about the primordial magnetogenesis. There are some proposal about that. The QED effect may explain the primordial magnetic field. So this is the end of my talk. Thank you for your attention.
Yeah, my question is about Hawking radiation and memory burden effect. So, as you know that these days people are also trying to uh, understand dark matter by means of primordial black hole. So I am wondering, in that context, when in your case Hawking temperature, effective temperature has been changed, so I would expect evaporation rate will change. So which way it will go? More faster evaporation or slower evaporation? And related question is memory burden, which tells that if entropy is considered appropriately, then suddenly decay rate will slow down. So can you comment?
Oh yeah, good question. Actually, once I suggested the idea that one obvious thing is that the Hawking radiation in the theater expanding universe differ from in the asymptotically pressed space-time. Now, the primordial black hole has the limit, the so-called the mass bound to be primordial, otherwise it evaporated earlier. That is well known. Now, for just imagine you have a charged black hole seeing down the story will be changed. When you have a magnetic black hole, I mean magnetic charges from the early Big Bang scenario, era, then black hole captures it, and you have a very stable magnetic black hole, just because the mass of black hole is so big, the mass of monopoles, magnetic monopoles, so big that emission suppressed. So I'm not good at cosmology and explain about the dark matter candidate for them, but from black hole physics viewpoint, then the magnetic black hole really stable at one loop. Not only Hawking radiation, but also the Shingle emission, because effective temperature is so small that no emission at all. The monopole anti-monopole pair production from the magnetic black hole almost suppressed. So if such a hypothetical black hole exists from standard particle physics model, then maybe a kind of candidate for dark matter. About your question about the entropy, I have never computed the entropy contribution for this charged black hole, but the Binny Carr and the original the PBH people already computed and put some constraint on the PBH bound, just because of entropy and also Hawking radiation. Now I will say that for charged black hole case, Shingle emission should be included. Now there's some scenario, feasible scenario of magnetic black hole from the standard particle physics model, now involving the GUT, GOT scale. When at GOT scale, monopole pairs are produced, down, probably captured by black hole, down it become magnetic black hole. And Maldacena recently just argue about that. Just combine the story. But about the emission from black hole at one loop quantum field theory, our result is very, very solid. Very, very solid. So I would say that.
The higher order curvature term, I think based on the scalars in the Einstein-Hilbert action, already we can use higher order curvature terms. But
oh yeah.
Point is, can you quantify these things in your approach? That
yeah,
features of the higher order curvature terms.
Yeah, that is very, very, very interesting question. That now in progress. Now, just because the Einstein-Maxwell theory, Einstein-Maxwell scalar theory, and including the back-nation problem, that is very challenging. But now, just because at tree level, I mean the emission formula, we did not compute the back-nation problem, but still we can combine all this together to explain about to answer your question in the near future, very soon. Yeah, coming very soon. Yeah.
Okay.
Thank you, sir. Very nice talk. So I just had one question when you previous slide, quite early. So you probably used the Matsumoto frequency, right? Beta in fifth or sixth slide, very early. Yeah, very early. After. So I can ask here itself. So I am asking that you probably wrote the same question for both scalar and fermions.
Yeah.
But if I understand correctly, the Matsumoto frequency would be different. Like, I mean, for scalar, the spin zero, it would be even, and for fermions, it would be odd. So the summation would, like the Euler summation, would be like different, right? I mean,
Yeah,
I guess.
yeah.
But you probably wrote the same expression, so that's why I got a little confused.
Yeah, yeah. Really super question. Now just imagine you have right degree freedom for scalar field and also fermion field. And when you combine together, this one will impact fraction that automatically the fermion degree freedom just cancel.
Oh, okay. So the calculation it
divergence
cancels.
terms. So it's a kind of natural renormalization whenever you have a proper degree of freedom for bosons and fermions, like supersymmetry.
Yeah.
Very interesting. Actually, we never emphasize that, but that is
Because that's why I got worried, because it should be odd or even for both
right,
scalars.
right. Actually, the sign differ, so the fermions and boson played a role of kind of some counter-subtracting divergence terms. Yes.
And just a small question for black hole in d theta, what should be the vacuum? Like, I know that for Minkowski or Rindler, it is the Unruh-Lewis vacuum. Like,
Yes.
which vacuum you will take to do the Bogoliubov transformation? Because it is the d theta background, right? So
Yes.
could you just comment on the vacuum? That's
Yeah. That is another super question. Actually, with my collaborator Chang-Hei Chan from Taiwan, that we are now computing kind of some the space-time geometry covering both of them. Lindler, smooth transition from Lindler to the ADS, or the theta for Navier black hole. We found out, not our concept, actually, that is the method introduced by Andy Strominger group at Harvard University. He has so many postdocs and PhD students. They found kind of some continuous and analytic continuation of two different geometry. So we are working on that problem. That is, I'm sure next time I'll explain that. I show that formula too. Yeah. So with that one, now we could complete evolution of child black hole for given mass and given charge, then Hawking radiation and shingle emission near the extreme limit and back and forth. Even explain about singularity problem, naked singularity problem, and possibly the information paradox too. So somehow very ambitious project. Yeah.
We have no time for other questions. So thank you so much, our speaker. Next talk, Suratna Das. Okay. Ashoka University, India. Some background checks for worm inflation. Also 35 minutes. Okay.
Hello? Yes. Okay. There's no change, right? Only here. Okay, take it. I can use the pointer. Yeah, I can use the pointer. Hey, pointer. Pointer. Okay. Okay. Good. Okay. Let me start my talk by thanking Professor Sami, Moyok, and Debotam. They had invited me to SGT many a times, but I just couldn't make it. But this time I'm here. Okay. Oops. Anyway, I hope it works. So as you can see that I'm going to talk about an inflationary scenario which I'll call as a bomb inflation, and it's not a name that I have given. Should I use even my screen is flickering, I don't know why. Okay. So as you can see that I have chosen a paper which is a little old. I published it in 2021, but I chose to talk about this paper. My screen, it's fluctuating. No, my screen itself is fluctuating. Screen time, screen time is. My screen time is really large. Okay. I'm using just a pointer. Okay. I think it's okay. Stable now. Okay, some stable inflation. So anyway, so I've chosen a really a little old paper which I published in 2021, but I chose this paper to present here because this is probably the simplest paper I have ever written in my life. Believe me, it requires only 2 differential equations and nothing more than that. Any high school student could have written this paper. And I wrote this paper. So bomb inflation was introduced or proposed in 1995. So I wrote this paper almost 30 years after that. And I don't know why no one before me could ever pointed this out, but this is a very nice physics. I wrote this paper with one of my collaborators, Rudina Ramos. So let me start. Okay, I mean, as Onyunda and other speakers had also talked about cosmology in the morning session, every cosmologist loves to start with this picture. So this is the history of the universe as we know, according to the Big Bang model, how our universe has evolved. So there is a Big Bang, and at the very beginning, we believe that in our universe must have gone through a very accelerated expansion, which is inflation, and my talk is written, is all related about this very early phase of this evolutionary history. And once inflation ends, then the standard Big Bang evolution starts, which is a decelerating expansion of the universe. So initially it must have gone through a radiation-dominated era. Radiation-dominated era because the universe was very dense, very hot, and the particles in those in the cosmic plasma were really relativistic at that time, and we call that era radiation dominated era. And as the universe expands, the universe cools down and the temperature drops, so the particle starts to become non-relativistic, and when the cosmic plasma can be treated non-relativistically, we call that a matter-dominated era. And after that, it had, as many of the morning session speakers talk about, it had entered a dark energy region where the universe is still, again, had started accelerating. But I'm not going to talk about dark energy at all. I'm going to talk about the accelerated expansion at the very beginning of this evolutionary history. But what is interesting during this matter-dominated era is this formation of cosmic microwave background. This is the time when the age of the universe was nearly 380,000 years. And what happened at the time that the temperature of the universe had gone below the binding energy of hydrogen. So electron and a proton can come together, bind together to form a neutral hydrogen, and the photons in this cosmic plasma will not have enough energy to knock that electron off from the stable hydrogen atom. And so stable nitrogen could form, and the moment stable nitrogen formed, the cosmic plasma becomes electromagnetically neutral. So as because the cosmic plasma becomes electromagnetically neutral, the photons cannot interact with the cosmic plasma anymore, and they become decoupled from this cosmic plasma. And this decoupled, so it's like two fluids. One is the cosmic plasma, and is the another fluid of this cosmic cosmic photons. And these photons today we are detecting in the cosmic in the microwave range. So we call it as a cosmic microwave background radiation. Why it is important is that because whatever have happened before this CMBR was formed, all these epochs can leave their imprints on the CMBR. Okay, so if we can study this, the features of these cosmic photons, we can say a lot about this inflationary phase which happened so long away before this CMBR was formed. So a little history. CMBR was detected accidentally by Penzias and Wilson in 1978. In 1965, and they got this Nobel Prize in 1978 for detecting this cosmic microwave background. What they had detected is a very uniform temperature of photons all over the sky of 2.73 Kelvin. So they saw this sky to be very uniform, but then people understood that it cannot be so uniform. It should have some fluctuations of the order of 10⁻⁵. And Kobe was the first satellite which was launched in 1992. It detected these fluctuations, so you can see that the sky is, so this is the background sky, and this is the sky 10⁻⁵ Kelvin below this temperature. And once you can probe that, you can see that there are these blue regions are the cold regions, then there are some hot regions. This is the galactic plane, so these are the galactic dust radiation, not the CMB radiation, but beyond that we can see the CMB sky, which is no longer uniform. And in 2003, WMAP again mapped the CMB sky very uniformly, and as you can see now more features can be seen. And once WMAP confirmed that CMB does have this tiny fluctuations, team from Kobe got the Nobel Prize in 2006. And today we have really mapped the CMB sky very precisely. This was the sky seen by Kobe. Then WMAP made a lot of progress, but now Planck has really made a lot of progress, and we can confirmly say that we do have mapped the CMB sky very precisely. So this is the current status of the CMB. CMB photons are not only, it's not only has this time temperature fluctuations, but these photons are polarized as well. There are two kinds of polarization. If you map these polarization patterns, then there can be patterns which are mirror symmetric, which we call as E mode, and there are patterns which are not mirror symmetric. Those patterns we call as B modes. So both these patterns can be very important in the context of inflation. So this is the CMB temperature, which background temperature, which Penzias-Wilson has seen. It fits a perfect black body spectrum, giving us the hint or confirming that these cosmic photons were in tight thermal coupling with the cosmic plasma before they got decoupled from the cosmic plasma. So this fits a very nice black body spectrum of 2.73 Kelvin. And these are these temperature fluctuations which we measure as correlation. So we look at the temperature fluctuations here and the temperature fluctuations there on the sky, and we plot this correlation between 2 points on the sky. And as because it has been mapped on a spherical sky, we decompose this 2-point correlation function in multipoles, and so these are this on the x-axis we have multipoles, and these are the amplitudes of these fluctuations, and these blue dots are the data taken by Planck with error bars. So you can see these dots are also with error bars. Only on the large scales the error bars are a little higher, but rest of the spectrum is pretty much very nicely detected by Planck. And this red dot, red line, which fits this data so well, is actually a prediction from inflation. So inflation can produce fluctuations in an otherwise very uniform FRW metric, and these fluctuations can actually inflation has actually predicted this kind of a spectrum, and which has been now confirmed by all observations. We can also talk about the polarization spectrum. So this is this temperature spectrum. Now, as because that we have plotted the polarization spectrum as well, this temperature spectrum got squeezed because the the polarization spectrums are orders of magnitude smaller than the temperature spectrum. So this is this temperature E mode cross correlation spectrum. This is E mode spectrum, and this is a B mode spectrum. And this B mode spectrum is very important for inflation, because this B mode spectrum, if detected, it has not yet been detected, this primordial spectrum, but once detected, it can very nicely predict at what scale inflation has taken place. Okay, so people are looking forward to detecting this BB spectrum. Okay, but let's talk about inflation, which is the main topic of my talk. So, of course, the theory of evolution is governed by, evolution of the universe is governed by Einstein's general theory of relativity. So, as we know, this is the Einstein field equations. On the left-hand side, we have Einstein tensor. On the right-hand side, we have energy momentum tensor. So, Einstein tensor tells us how the geometry of the space-time evolves, and T mu tells us how the matter evolves, and this whole equation tells us that the evolution of the geometry and the evolution of the matter are coupled, and evolution of matter affects the evolution of the geometry and vice versa. Okay, and in cosmology, this space-time metric is given by the Friedmann-Robertson-Walker metric, which is basically like a Minkowskian metric, except that there is a time-dependent factor sitting in front of the spatial part, which says that the universe is either expanding or contracting. It can be either way, but observations, we know from Hubble's observation that, we have an expanding universe. And so this time-dependent factor is known as the scale factor. And during inflation, as I said that this inflation is a very brief epoch when the universe had expanded exponentially. So the scale factor is nearly an exponential factor, and this h is known as the Hubble parameter, which is basically telling you how the scale factor is evolving. So h is a dot upon a. Okay, and the T mu part here. So now we need a matter which can drive such an exponential expansion. So this T mu should be some exotic matters, and this exotic matter is a slowly rolling scalar field, which we call as an inflaton field. So how can, is there a question? Oh, sorry. So how can a scalar field drive such an exponential expansion? First of all, it has to slow roll. Slow roll means that the potential energy should be much more higher than its kinetic energy, so the potential has to be very flat. so that the kinetic term of this field is very small, and on this flat region where when this scalar field is slowly rolling, it can drive an exponential expansion. I'll come back to it. And the flatness of the potential is given by these two slow roll parameters. So you can see this epsilon v and eta v. Epsilon v is the first derivative of the potential and eta v is the second derivative of the potential. Both has to be much smaller than 1 so that the potential is very flat and inflation can take place. And once the potential becomes very steep, you can see at this point inflation ends. But as because inflation is an exponential expansion, if there were any energy density before inflation started, all those energy densities will be exponentially diluted away. So to enter a radiation dominated epoch, one requires to reheat the universe, and reheating requires such a dip in the potential or a minimum of the potential where the scalar field can oscillate and decay to radiation so that the universe can enter a radiation dominated epoch. So this is the most standard picture of inflation, that you need a very flat potential and then you require a bottom of the potential. So flat potential, flat region to inflation to take place, and a bottom of a potential so that inflaton can decay and gives you radiation, so that the standard Big Bang evolution can take place. Okay, I'll come back to this picture again. And as because this inflaton field is a quantum field, it has this background field which slow rolls and gives you inflation, but it also has quantum fluctuations. And these quantum fluctuations can seed fluctuations in the background geometry, because Einstein field equation tells you that the matter and the geometry are coupled. So once there is a perturbation in the metric, there will be a perturbation in G mu nu. But now you are perturbing a metric, which is a tensor, so you will get all sorts of fluctuations, not only scalar fluctuations, but vector fluctuations and tensor fluctuations as well. The scalar fluctuations are actually get imprinted on the CMB sky. So CMB gets its fluctuations because of the scalar fluctuations which get induced in the background geometry. Okay? But we are not going to talk about the perturbation of inflationary theory at all in this talk, but what we will be interested in this background evolution of both matter and metric, okay, during inflation. So first of all, the most important point of today's talk is how inflation ends. So inflation has to end so that the universe can enter a radiation dominated epoch. And there was a problem initially with the inflationary phase, which is known as the graceful exit problem. So the inflation should gracefully exit to a radiation dominated epoch so that the standard Big Bang evolution can take place. Okay? So what is graceful exit? So as I said, inflation again is a phase when the universe has expanded exponentially for a very brief period of time. So these are the two Friedman equations. The first one is proportional to the energy density, and the acceleration depends on both pressure and energy density of the matter. But as because in cosmology we always talk about a perfect fluid can be written like this, that the pressure is proportional to its energy density, and this omega is called the state parameter. So this state parameter is sitting here, and as you can see that to have an accelerated expansion, we need A double dot to be positive, and A double dot can only be positive if omega is less than minus 1/3, right? So if you want to have an accelerated expansion, you need a fluid with omega less than minus 1/3. And cosmological constant, whose equation of state is omega equal to -1, is a perfect fluid to drive inflation. But the only problem is that you cannot end inflation with cosmological constant. So there won't be any graceful exit. Okay? And that's why we need a slowly rolling scalar field so that we can end inflation. So if you have a scalar field, and it helps in graceful exit, because if you have the energy density and pressure of the scalar field, it has a kinetic term and a gradient term and a potential term. Similarly, the pressure also has a kinetic term and a potential term and a gradient term. If you let the kinetic term dominate, then you can see that the state parameter will be 1. So a kinetic energy dominated scalar field cannot drive inflation. then if you let the gradient term dominate, then you can get a fluid with negative pressure, but it is not enough to drive accelerated expansion because you need omega to be less than minus 1/3. So with that also you cannot drive inflation. But if you now let the potential energy to dominate, then you can basically satisfy all the condition and you can have a accelerated expansion. So the potential needs to be very flat so that the kinetic term is negligible, and this is called the slow roll of inflaton on its flat potential. And the slow roll parameter, as I had said, should be much smaller than 1 during inflationary phase. Okay? So this is basically a slow roll approximated Klein-Gordon equation which tells you that 3h phi dot is minus v phi, and once you imply that epsilon has to be much smaller than 1, you ensures that your kinetic term is much smaller than your potential term. So inflation ends when the potential becomes steep and your slow roll parameter becomes of the order of 1. So this is the most standard picture in which a standard inflationary phase can end. So you should have a slow roll parameter much smaller than 1 where inflation can take place, and then this epsilon should grow, and it should grow and become 1 so that inflation can gracefully exit. So you need a potential where the at some point of time the slow roll parameter grows or the potential becomes steep. So this is a very mundane kind of a picture where you can have a gracefully exit in standard cold inflation, and that gives you a very restricted form of the potential, that you need a flat region and you also need a bottom of a potential where it can reheat. So you can see that the form of the inflaton potential is quite constrained so that one can have a successful inflation, but not anymore if you consider a variant scenario which I call as warm inflation. What is warm inflation? So warm inflation, so the standard inflation now I'll call as a cold inflation, where again you have a flat region and there is a bottom of the potential. But warm inflation is something where reheating takes place during inflation itself. So this inflaton field is coupled to a radiation path and it continuously dissipates its energy to the radiation path so that one can maintain a constant, not dominant one, a subdominant one. You can maintain a subdominant radiation path during inflation. So if the inflaton field is not dissipating its energy to the radiation path, the radiation which were there at the beginning of the inflation would have exponentially diluted away. But as because the inflaton is dissipating its energy to this radiation path, you can now maintain a constant radiation path. And the good point is that when inflation ends, there is a existing radiation path which can start the radiation dominated epoch. So what you don't need in this warm inflation is this reheating phase, because reheating is basically happening during the inflation itself. Okay? So now this is the equation, Klein-Gordon equation in standard cold inflation, but in warm inflation you have both the inflaton fluid and a radiation fluid, and both are coupled. This epsilon is this dissipative term through which inflaton transfer its energy to this subdominant radiation path. Okay? So why warm inflation? Warm inflation has quite a nice good features over cold inflation. First of all, it doesn't require a reheating phase. We do require a reheating phase, but we maximally don't know what is the dynamics of reheating, because reheating doesn't impose any signature on the CMP. So you cannot say what kind of reheating mechanism is taking place. So reheating phase in cold inflation is absolutely needed, but you cannot say what kind of reheating dynamics has taken place. So warm inflation actually doesn't require such a reheating phase. Secondly, as our previous speaker was showing, that this is this 2 dots of Starobinsky inflation, but if you want to have a very standard lambda 5/4 potential, you can see that it is nowhere in this picture because this is ruled out by this tensor to scalar ratio versus NS plot. Okay? So very standard particle physics potentials are ruled out and cannot play as a inflaton potential, cannot play any role as an inflaton potential. However, that lambda 5/4 in warm inflation can actually, so these are the two dots with lambda 5/4 in warm inflation, and you can see that even with a small amount of dissipative coefficient, you can have a, you can make lambda 5/4 compatible with the observations, because in warm inflation, this tensor to scalar relation, which I didn't talk about much in this talk, but it is suppressed, okay. So, and also in strong dissipative warm inflationary models, they prefer small field inflation, which again is supported by the present data, and there are other advantages of warm inflation which I'm not going to get into at this moment. But what I want to point out is that this graceful exit in warm inflation is much more complex than it was in cold inflation, as because now you have this dissipative coefficient. So if I just go back a little, you can see now this inflaton equation has two frictional terms. One is this one, 3h phi dot. This frictional term is present because of the expansion of the universe, and there is another friction term sitting in this equation of motion, which is due to the dissipation of the inflaton field. Okay. Now there are two competitive dissipative terms which is governing the evolution of the inflaton field, and depending on which of these, so Q is a dimensionless parameter, which is the ratio of these two dissipative terms. One dissipation is due to this is due to the dissipation, and this is due to the Hubble expansion, okay? And this Q is sitting in this equation of motion. And once you derive your slow roll condition, you can see that in warm inflation, because of this modified dynamics, slow roll inflation can take place in warm inflation when epsilon v is not much smaller than 1, but much smaller than 1 plus q. And warm inflation ends when epsilon v becomes 1 plus q. Now, you have two dynamical variables, both epsilon v and q, they vary with time, okay. So, both are evolving with time. So, there are many ways you can gracefully exit in warm inflation, okay. Let's, for that, first of all, you need to know how Q evolves. For you to know how Q evolves, you should have a form of this dissipative coefficient, and there are many warm inflationary models, and one can actually write a very general form of the dissipative coefficient. Dissipative coefficient in general depends on the temperature of the radiation bath as well as the inflaton field. So, you can parameterize your dissipative coefficient like this, and once you parameterize your dissipative coefficient like this, you can see this is how your epsilon v is evolving with time. So, n is called the number of E folds. It is just one way of keeping time in an exponentially expanding universe, nothing else. So, you can treat it as a time. So, you can see that this epsilon v is also evolving and q is also evolving, okay. So, this p and c are sitting here depending on what kind of epsilon you are choosing for your warm inflationary model. Now, how many, yes, I'll be done. So, how many ways you can end warm inflation, or you can gracefully exit from warm inflation? So, remember that warm inflation takes place when epsilon is much smaller than 1 plus q, and warm inflation ends when epsilon becomes equal to 1 plus q. So, let's take a scenario, let's take a potential where epsilon is constant. So, this is one scenario where cold inflation can never end, because to cold inflation to end, you need epsilon which should become 1 at some point of time to gracefully exit. So, this is a condition where cold inflation can never end, but warm inflation can end, because if epsilon is constant, you choose your epsilon in such a way that your q is decreasing over time. So, at some point of time, 1 plus q will become of the order of epsilon and warm inflation can end. So, now you can see that you can have much more different kind of potential in warm inflation, which was not acceptable in cold inflationary scenarios. Well, if you have a potential where epsilon grows, which is good for cold inflation, you can always end cold inflation in a potential where your epsilon parameter grows. But in warm inflation, you can end it in 3 ways. First of all, you can choose your epsilon in such a way that your Q is constant. So if Q remains constant, your epsilon is growing, and at some point of time, you can end your warm inflation. This is one way. Another way, if your epsilon is increasing, but 1 plus Q is decreasing, then also you can meet this condition to end warm inflation. There's another way. If both are increasing, but if 1 plus Q is increasing with a much smaller rate than epsilon, then also epsilon will at some point of time take over 1 plus Q and your warm inflation in end. The only way in which case you cannot end warm inflation, even if epsilon is growing, is if your 1 plus Q is growing faster than epsilon. So there is a situation where you may not end your warm inflation, even if you have a potential where your epsilon is growing. Okay? Again, you take another potential where your epsilon is decreasing. This is also bad potential for cold inflation, because you cannot end cold inflation at all in such scenarios. But in warm inflation, you can gracefully exit from such an inflationary phase, because if epsilon is decreasing and your 1 plus Q is decreasing faster, then also you can meet this condition at some point of time, and you can end warm inflation. So the message I want to give you that warm inflation is much more versatile. It can accommodate much more variety of potential which are not suitable for cold inflation. Okay? But the thing is that not only this analysis tells you that in warm inflation you can actually have, if you want to have graceful exit in warm inflation, then there are certain combinations of potential and epsilon which works. Not all combinations of epsilon and your potential will work, right? So it put constraints on the combination of the inflaton potential and the form of the dissipative coefficient. So this analysis tells you that not all potential and not all dissipative coefficients are compatible. Okay? So let's say one example. So let's say if you have such a polynomial potential phi to the power n, and if you have your epsilon, the form that I had already shown, then you can see that these white regions are where warm inflation will never end. Such as if you take a C equal to 0 kind of epsilon, where the epsilon doesn't depend on the inflaton field at all, it only depends on the temperature of the radiation bath, then if your T is minus 2, let's say T to the power minus 2, then lambda phi fourth is a bad potential. Even lambda phi fourth you cannot end inflation. Okay? Similarly here with C equal to 2, there are certain combinations where warm inflation cannot end. So even before going to the perturbation theory, before going to looking at the spectrum that warm inflation can generate, you can look at the background equations and constrain your form of potential and the dissipative coefficient so that you can have a really valid warm inflationary model. So thank you.
Question, please. There.
End of inflation always means epsilon has to be equal to 1, isn't it?
Well, you can play the same game with eta.
Okay.
That will again give you some constraint.
No, but in any way, epsilon is rate of change of the Hubble parameter, right? Logarithmic rate.
No, these
So
are the potential. These are not the Hubble slow roll parameter. These are potential slow roll parameter. That's why it put constraints on the potential only. I'm not talking about the Hubble slow roll parameter at all.
Okay, and what is the relation between these two? In warm inflation?
In warm inflation, epsilon H is equal to epsilon V by 1 plus Q.
Okay.
Okay.
Okay. The last question, okay?
So let's say I have these CMB maps, or let's say galaxy maps, fine. And all these CMB or galaxies, they need a primordial power spectrum. Means
Yes.
Like, okay, so AS k to the power ns minus
Yes.
1. Now, is there anything for warm inflation that I can have a specific feature in CMB or galaxy, and I see this thing and I say that, okay, this is warm inflation?
Yes. not in 2-point correlation function, but in non-Gaussianity. The non-Gaussian features in warm inflation is completely different from cold inflation features.
No, but non-Gaussianity is a bit tricky because if you want to see the non-Gaussianity,
2-point correlation function is the same. Umang is going to talk about this fitting the power spectrum in CAM.
Non-Gaussianity is tricky because if you want to see really non-Gaussianity in galaxy, especially fine. It depends upon whether you are taking the non-Gaussianity coming from inflation or from
so
galaxy.
primordial non-Gaussianity, the features are very different.
So that's what I'm saying. Primordial non-Gaussianity.
One is primordial non-Gaussianity, the other is the tensor to scalar ratio. The tensor to scalar ratio with the same amount of same potential, tensor to scalar ratio would be much order of magnitude smaller than cold inflation in warm inflation.
Okay. So tensor to scalar ratio is already very, very small, means like
yes.
that the lower, I mean the upper
yes.
limit has been already very
but
small.
If you really detect, so warm inflation generally gives you a tensor to scalar ratio of 10 raised to the power minus 4. If you detect something above that, then warm inflation models will be in real soup.
Means Starobinsky model also gives very, very small.
Yes.
Okay.
No, it's all right. We can discuss later during the tea.
Actually, we shift and already 20 minutes, so no tea break.
Yeah, that would be nice.
Okay, our last talk in the afternoon session. Vani Brata, please help me. Mukhopadhyay.
Yes.
Yeah. Well, energy extraction from a black hole and powerful astrophysical jets, theory, simulation, and observations. Anyway, it's 40 minutes because.
And you'll give me. I'll speak only for 35 minutes. Okay. Yeah, you give me 5 minutes warning at 30th minute. Okay. Yes, I'll put my stopwatch also. Okay. It is really my great pleasure to be here. Special thanks goes to Professor Sami, who essentially affectionately dragged me into here because mostly the talks are in cosmology. Perhaps my one is one of the very few, of course it has cosmological flavor, but it is primarily astrophysics, and one of the very few, I think nearest one is by Professor Indrani Banerjee. Yeah, first time I was in this university. I had not had chance to see around, but whatever I had looked at looks very nice. Really my pleasure to be here. Also my further pleasure is when I see the program, I see my second student is also one of the plenary speaker, and my, as of now, second last student is also one of the invited parallel session speaker. So really it is my great pleasure to be here. So title again, Sami suggested. So energy extraction from a black hole, and I'll try to see why this is very important topic. First of all, I'll try to motivate observationally. Then there are interesting theory which supports, and then simulation will try to put the nail in the current scenario. The work is being done primarily by two of my current students, Mayank and Rohan, one of my ex-student, and also Kaushik here, one of my ex-student, and also two of my students contributed, not directly but indirectly. I started working in a similar field with Shubhranshu, my first student, and also Tushar had contributed the underlying theory. Then I started simulation. Actually, Kaushik started the theory with me, then Tushar took over, and then simulation I'm talking about today. All right, from the very basic. I'm sure many students are there. They are maybe again primarily cosmologists. Let me start with the very basics of energy extraction from black hole. So black hole's gravity is extremely high, we know. Even light cannot escape. We have been hearing several since our young days. And what is the energy release? So let's consider this simple diagram. Black hole is sitting here. There's a companion star which is rotating. That means the matter on the surface of the star has tangential velocity and gravity acts radially. So matter which is being pulled up by the black hole takes this resultant and falls through a spiral path and forms a disk-like structure. This is accretion disk. In absence of black holes, direct identification, people look at the accretion disk, light from the accretion disk, and people try to understand the existence of the black hole. Now, when matter falls, what happens? Black hole's energy, potential energy barrier is getting converted to kinetic and heat energy. And when matter falls close to the black hole, innermost stable circular orbit, energy per unit mass turns out to be 10 to the power 20 ergs per gram. So huge, it is even greater than nuclear energy. In other language, the rate of infall of matter, if I assume 0.1 times Eddington infall of matter, Eddington accretion rate, Eddington accretion rate is typically the rate, the bound, typical bound, bound of infall of matter, infall rate of matter, which is same as the star, the rate at which star is emitting wind from the surface. So that is a bound, typical, is not a real bound. And if 0.1 Eddington accretion rate is the infall rate, what happens, the luminosity, when this matter in the black hole of 10 solar mass comes to this matter is coming at the ISCO for 10 solar mass black hole, luminosity is by 38 arcs per second. Again, about 5 orders of magnitude higher than sun's luminosity. All argue that black hole has enormous power. From very theoretical point of view, black hole alone, without any environment, the rotational energy, extractable rotational energy could be up to 29%. The maximum spin of the black hole I consider A in gm/c unit Kerr parameter. And for 10 solar mass black hole, this 29% turns out to be 10 to the power 54 ergs. Huge. So black hole system is essentially a huge reservoir of energy. Question is how to tap the energy. That's a big question. So there are phenomena. Whenever black hole is there, in majority of situation, you find a powerful jet from the accretion disk. From the very inner region, when matter is completely to be sucked up, but matter is coming out in place of completely getting absorbed. Why it is coming out when gravity is most powerful? This is a Hubble Space Telescope image. This is another phenomenon, quasi-periodic oscillation. If you look at the X-ray photon count as a function of time, you go to the Fourier space, you find some broad end peak, which is quasi-periodic oscillation peak. Those are the typical characteristics of black hole's presence, black hole. So with this, I'll try to motivate you. Basically, I'll try to establish in next half an hour that all phenomena, what I have been showing you, are trying to address, are hydromagnetic effect, not only hydromagnetic, general relativistic hydromagnetic effect. I'll establish, but just to motivate you, for young students particularly, I'll start with a movie. What you will see, this is a torus. Black hole is sitting here. And due to black hole's powerful gravity, torus will be flattened, which will basically supply matter, which form a disk-like structure. And then the charge system, charge particle is moving, will be creating electromagnetic field, which will eventually produce powerful jet. I'll explain everything, but I'll start with a movie. I think I have to come out of the slideshow mode. See, it will now start. The green color, magnetic field lines, you will start seeing. So magnetic field lines are coming out. I'll explain why it is happening. Basically, magnetic shear, B phi BZ term, and then blue, which is a charged matter, which is climbing up and down through. So now torus is flattened disk. So basically the disk, accretion disk, close to the black hole. Why close? I'll explain. Basically Argo region energy is being tapped, and that basically powerful jet. So I'll try to explain in next 28 minutes or so origin of this and try to convince this has to be general relativistic magnetohydrodynamic process. Okay, let me go back to the observational motivation. So Cygnus X1 is a famous black hole, and this black hole source is exhibiting a spectrum which has several components. One is black body like region, which is thermal spectrum at low energy, often called soft spectrum. Another part is going all the way up to 10 to the power 4 keV, very hard, high energy, non-thermal region. So I have to explain, successful model should be explaining this observation exhibiting soft X-ray, hard X-ray and some intermediate region. So I'll show you that to explain this hard X-ray region, I require advection, and soft X-ray region, I'll require Kepler's law, means centrifugal force and gravity are locally balanced. I'll explain one by one. Overall, okay, apart from Cygnus X1, also GRS 1915 plus 105 is another source which also exhibits similar property along with quasi-periodic oscillation. So overall, I need advection to explain this part, which is making system sub-Keplerian. I need Keplerian part also, which explains this, which does not have advection, and I necessarily require magnetic field that will help to not only infall, which will also help to kick the matter out. I just showed the movie. I'll explain physics. So disk outflow, symbiotic exploration must be done. So infall, outflow together has to be done. So another observational motivation, this is a Q diagram, famous Q diagram. See, this is intensity or luminosity as a function of X-ray energy. Okay, why I am telling X-ray? Actually, for black hole of mass, few times mass of the sun, up to 10 solar mass, say, for example, when potential energy is converted to kinetic and heat energy, the energy release is in the X-ray regime. So stellar mass black hole, which is having mass few times mass of the sun, is the emitter of X-ray. So this is the X-ray energy, low energy, high energy. When energy is high, it is found that jet is formed. The jet I showed you as a movie, that jet is generally exhibited when disk is emitting high energy X-ray and luminosity is low. Disk luminosity is low. Jet may have power, but disk itself, the disk-like structure I showed, that has low luminosity, but jet has strong power. Now, as matter supply increases, basically what happens, hard X-ray means matter supply itself is low. Low matter supply will have hardly have chance to interact with the radiation therein. So system is not thermalized. That is why hard X-ray, non-thermal X-ray. As matter supply increases, what happens? Density increases, matter radiation are in thermal equilibrium, system becomes the soft state because whatever heat is generated, that immediately radiated out. And then this becomes geometrically thin. Here it is hot. Heat cannot be emitted, held, halted, I mean it is stored there. System becomes puffy, hot, this region, and that gives powerful jet. But when this becomes thin, heat is radiated out, then there is no jet. This is the intermediate region, could have some strong superluminal ejection, not really strong collimation. So hard state, soft state. And again, if you further keep increasing matter supply, which is accretion rate, this is the region. Here we see the supply of matter has to be supercritical, super Eddington. So radiation trapped system. So this is the cycle goes on, hard to soft, Q diagram. Also the famous theory, you see this is the famous, this is a thermal region of the disk. Here I am plotting accretion rate as a function of the column density. Here, this is a Sakura-Suniev, famous Sakura-Suniev disk we call, people who are not in this field. When disk is in the thermal equilibrium, relatively cold, what I showed basically this region, centrifugal force is balanced by the gravity, this region. This region on the other hand, that has two branches. So if accretion rate is high, what happens? Density, for a given accretion rate, if density is high, log scale, this term dominates. This advective factor becomes negative, that makes the disk unstable. So to stabilize, you have to have strong radial motion. That's why advection is very important, and this eventually makes system of high energy emitter, hard X-ray emitter, non-thermal, because before system is unstabilized, destabilized, matter is moving radially and engulfed by the black hole. So system eventually stability can be recovered. So strong radial velocity is very important. And this is a radiation trap system. So basically this region and this region, remember, this is the upper region and this is the lower region. They are basically connected. Slim disk and this is the sub-Keplerian disk. So actually one straight line. There is a discontinuity. This is the thermal disk. This is non-thermal. This is also slim disk, geometrically thick. This also produces jet. This also produces jet. It is all the parameter space, accretion rate, and the density. So we'll try to understand this observation. This is observational data, and models are put in at various points. Keplerian disk is a model. Sub-Keplerian disk is a model. Slim disk is a model. So this is a line, model lines. We are trying to, next 20 minutes or so, I'll try to understand how exactly this model plays. I mean, various points, like here, there's simple energy momentum balance. When I am in the Keplerian region, like that means you can think of a system is emitting soft X-ray, thermal, black body radiation is the spectrum. Then these terms are negligible. Centrifugal force is balanced by the gravitational force. On the other hand, when you are in the hot regime, advective regime, or this slim disk regime, supercritical, then these terms dominate. This term relatively weaker. So strong advection and pressure support is making system non-Keplerian and advection dominated, which will stabilize at the hot system. We'll try to understand the physics detail. So I think we have had some idea, I have given some glimpse as of now, what actually accretion disk is and how accretion disk structure, geometry is determined by the underlying matter supply rate, the cooling rate, and so on. Now this is important related concept, because at the center of the accretion disk, argosphere, black hole is sitting, and rotating black hole has this region called argosphere region. So what is argosphere region? This is a oval shape region, ellipsoidal. This is a region when GTT is 0 for students' convenience. There is a static limit. If matter reaches in this region inside, then matter cannot be static. So that region is called argosphere. What happens if matter, say matter with energy U1, reaches here, and due to black hole's effective potential, it is getting reflected, transmitted, and so on. So if in this region, reflection is negative, means matter is eventually lost by the black hole's gravity, and other part, which is transmission part of energy E3 coming out, it takes extra energy from the underlying reservoir, argosphere reservoir. And as a result, transmission coefficient is more than 1, reflection coefficient is negative, total is unity. So that is basically, again, basic building block of energy tapping, basically Penrose process. The efficiency of Penrose process, again I am repeating, matter is split into two parts. One is captured by black hole, another come out with additional energy from the black hole's stored energy with transmission coefficient higher than supply, and efficiency could be up to 20% depending on the spin of the black hole. So that again tells ergosphere of rotating black hole itself is a powerful reservoir related to super radiance of the energy. Question is how to siphon energy. Same question I started with the second slide. How to siphon the energy? Answer is magnetic field. So I think I have, in several angles, I have now told you, I have been able to convince you that accretion system, black hole and environment is basically reservoir of energy. How to siphon the energy? Now let's consider system is magnetized, or matter which is flowing is charged. As because gravity is pulling matter, along with matter, magnetic field is also dragged. So something called flux is frozen. If conductivity is very large, matter and magnetic field are coupled together. And as matter is being pulled in by the gravity, along with matter, magnetic field is also dragged in. And as matter accelerates close to the black hole, magnetic field also accelerated fashion accumulated close to the black hole. And if geometry is such that is a poloidal magnetic field, like this, kind of stick, and disk is rotating also, that means corkscrew-like structure forms. And that basically is producing magnetic shear B phi Bz primarily, then also BR/Bz. Those are the primary shear or magnetic tension component that is helping to pull the matter. So basically it is like in my childhood days at least, there's in the several at least rural area of country, well full of water. But how to get the water? Basically people used to take a bucket with a thread, they used to put inside and take the water from the bucket, from the well with the bucket. So it is basically black hole system is a reservoir of energy. To get the energy or to siphon the energy, we basically have to put a bucket with a thread, have to take it out. That's the magnetic field lines. Again, I'm repeating, outer region, this poloidal field lines are there due to black hole's rotation, they're twisted and that takes energy out. From inner region, as ergosphere is present, matter, the system, matter therein is necessarily rotating. So matter cannot be static, and very fast is twisting of the matter, fast twisting of the magnetic field lines, matter is climb up, and that exactly you saw in the second movie. So this is outer region, okay, red is outer region due to disk rotation, and green is the inner region, which is due to ergospheric rotation. And either of the cases, so outer region, which is called Blandford-Payne process, which is not necessarily general relativistic, but inner region called Blandford's-Naik process, I'll come in a few minutes, little detail, which is necessarily general relativistic, which is due to ergospheric effect. And so again and again, system may be huge reserve of energy, but to tap energy, I need magnetic field, and magnetic shear plays very important role. For that, you need specific geometry. So basically, the power of the jet, two terms are involved. One is the magnetic flux. I just now showed the magnetic field lines. Flux is important, and black hole spin. If either of them is zero, no power. Of course, non-spinning black hole, non-magnetic, weakly magnetic black holes have jet, but those are different mechanism, weaker jet. It is believed that most powerful jets are due to coupling between magnetic field and rotation of the black hole. Now, I have been telling magnetic field is important. So question is, what are the observational evidences of strong magnetic field? It is just mathematical fantasy. Actually, again, I'm considering one of the favorite source, Cygnus X1. Cygnus X1 is a stellar mass black hole of mass 14 solar mass, and it is also exhibiting jet. From the polarization of the jet, one can recover footprint of the jet, which is a disk, is having field about million Gauss. And if I extrapolate this million Gauss field at the disk for supermassive black holes, say blazar, AGN of 10 to the power 9 solar mass, what is the extrapolation? Basically, magnetic field scales with square root of the density of the system. And density of the system scales with mass supply rate and the mass of the inversely mass of the black hole. So if mass supply rate is same and mass of the black hole is 10 to the power 8 times higher, magnetic field goes down, and that tells that for supermassive black hole, field could be 100 Gauss, and indeed many Fermi blazar, the supermassive black holes in the Fermi satellite basically indicate that field could be 10 Gauss at the top, which is away from the disk. So in a region, due to again frozen flux, field could be easily 100 Gauss. So observationally, it is evident, at least for stellar mass black hole, millions Gauss field is there. So whether million Gauss is enough, that's the next question. So for that last part of the talk, I'll do numerical simulation. I hope I have been able to convey you that so far black hole is enormous reservoir of energy. Black hole is associated with the accretion disk. Black hole accretion disk together often form a reservoir. To tap the energy, I need magnetic field. These three things I think I have conveyed so far. So theoretically also proven, I had some theoretical evidences. Now how to simulate, how to see, can I visualize this? For that I do the simulation with my students. Remember, in this simulation I'll consider two regimes. So magnetic simulation. So magnetic simulation means it is involved with magnetic vector potential. That's one of the important ingredient. Two vector potentials are considered. One corresponds to slow accumulation of matter. I had been telling a few minutes back, right? Matter is coming in due to strong gravity. Along with matter, magnetic field is dragged in. So this dragging, the way at which magnetic field is attached to the matter, and it's a geometry determined by vector potential. This is a slow accumulation of matter. This is a fast accumulation of matter and magnetic field. So this is MAD, magnetically arrested disk. This is SEN, standard and normal accretion. Please remember in next 7 minutes, MAD and SEN. MAD is powerful supply of matter, SEN is slow supply of matter. Please remember these two. And there are various black hole spin I choose, 0 spin, 0.5 spin, 0.93 spin, various plasma beta. Plasma beta is gas to magnetic pressure ratio. So larger the plasma beta, smaller the magnetic field, and so on. With this I am doing the simulation. So now I'll run 3 simulations. One is SEN, slow supply of matter with 0 spin. MAD, strong higher supply of matter, 0 spin. You will see, just because MAD, no black hole spin, due to strong magnetic field, strong accumulation of matter, it will have faster infall and faster accumulation of magnetic field and faster corkscrew-like effect and faster ejection of matter. And here both are MAD, but this is in addition high spin. You will see this will be faster. It is slow, fast, faster. I'll start the movie. See, all have same magnetic field at the beginning. See, this is all the wedge-shaped region, all the way reaches the black hole. Here, see some eruption takes place. Here eruption is stronger. See some eruption, huge eruption. Compared to this, no eruption, eruption. MAD 0 spin, SEN 0 spin. But MAD 0 spin, MAD 0.93 spin. Huge eruption. Here weaker eruption up to 30. So it is basically magnetic field is accumulated, and as magnetic field accumulated, is produces a wall. So matter is not able to go into that wall. So it is halting the matter, and then once enormous matter is accumulated, it is removing. Basically B phi BZ quantity. And here you see, even up to this 30,000 time step. So this is never showing any eruption. Matter is always going to the black hole. This fellow is oscillating in and out, but slower than this fellow. This fellow's eruption sometimes going all the way up to 60 gravitational radius. So this basically tells how magnetic field along with spin of the black hole together control the accretion mechanism, and more powerful magnetic field is along with powerful black hole spin, maximal possibility of energy extraction, and that's it. So next question is, what are the implication, immediate implication? I'll show immediate implication through an unusual source. Now it is not unusual, last 10 years or so it has become usual, but very strange source, ultra-luminous X-ray source, X-rays in hard state. Still it is not well understood that whether, no, I think I started at, I am 35 plus 5. No, he's saying 5 minutes. So according to my stopwatch, 27 minutes, 35 seconds. So, so ultra-luminous X-ray source, which is still not known to have whether black hole or neutron star for sure, and its luminosity is very high compared to many other conventional accreting systems. More importantly, this source is shown in hard state. Hard state means matter supply is less by definition. As I showed at the very beginning that hard state means, if you remember, hard state means this is the region, intensity is low, so matter supply is low, and that means this is the low accretion rate, hard state. This is a soft state, high energy. So basically I am trying to say this is ultraluminous X-ray source in hard state, low supply of energy. Still how it is producing high luminosity, that's a big question. People argue maybe mass of the black hole is high, or accretion rate could be very high, which is energy is basically accretion rate is high, and basically that high accretion rate is producing extra luminosity. But hard state is difficult to believe to have high accretion rate, and intermediate black hole has its own problem. I'll not go into detail of that. So basically it has strict upper limit of the mass accretion rate. So you have to have advection to explain this source, and these are the various energy spectrum, observational spectrum. You see, it has a power level. In the black body is like this, right? So that means gamma is very large. Then it will be falling fast. But here gamma is very small. Gamma is very small. So it goes all the way like this. So power law tail, non-thermal tail. So that only can be explained by restrictive mass supply rate, restrictive accretion rate. How is it possible? So our argument is this high luminosity at low accretion rate is due to powerful magnetic field. Is it possible? Let's see. So this is the power as a function of radial coordinate, and this is the region of hard ULX band. So my model should be able to explain the luminosity or power in this region. If I consider that black hole spin is 0, whether mad or sane, luminosity cannot be explained. But if I have black hole spin 0.93, mad is very much explaining, and efficiency, which is the infall rate minus outflow rate by equilibrium infall rate, which is efficiency, could be even up to 1200%. Basically the Penrose process, magnetized Penrose process. And sane also could do, but MAD is very much in the range of the observed luminosity. So basically this is a theory. So basically magnetized Penrose process, efficiency has two parts. One is non-magnetic part, another is magnetic part. So this is the generic system. If you have a situation when that you have electromagnetic force is dominating or inertial term, then this reduces to this simpler form called exactly magnetic Penrose process in the modified form. Basically, Nares, Dadich, and Tursunov had some work also of late, apart from Blandfors-Naik, originally pioneered. And if Q3 is larger than Q1, it can have large efficiency. Other regimes are also there, like initially particle is neutral in charge and split into two charged particle, and this is the efficiency. But all I'm trying to say, this efficiency can be explained, this efficiency, why it is more than 100%. I'm trying to, not even 1000%. How is it possible? It can be understood from the theory. Magnetic Penrose process. So basically, I'll just summarize the various flow profile. So this is the sane, which is more quasi-Keplerian, soft state-like system. Angular momentum is similar to Keplerian angular momentum, and geometrically thin. H by R you see quite small, geometrically thin disk. But here, geometrically thick disk, you see H by R close to 1, and lambda by lambda is significantly smaller. That means it is advective. Angular velocity is very small, it's a radial velocity supported flow. So this is more like Adolph-like, this is Keplerian-like. This is a magnetic field, you see, this has very strong B theta poloidal field compared to this. This is again, as I said, poloidal fields are anchored, and due to rotation, corkscrew-like structure forms, and that plays the role of pushing the matter out. So now this is 2D. In last 2.5 minutes, 3D. What is the 3D picture? Which is more realistic perhaps? I don't know. 2D also could be realistic because system geometry is such that it could be, may not allow to break axis symmetry. But if you allow to break axis symmetry, what is the flow? Here I consider two situations, low magnetic field, high magnetic field. Black hole spin is very high. Now you see, this is high magnetic field. This is a zoomed in view. This is also zoomed in view. Here you see throughout almost symmetric flow. But here when field is very strong, you see asymmetry comes. And again, the matter will be completely filled in at some point due to stronger accumulation of magnetic field along with matter. It will create barrier. Then at some point, due to strong field, matter will be ejected out due to eruption. Again, matter will be filled in. But importantly, symmetry is broken because axis symmetry is broken in any case. And yeah, so you'll see some eruption immediately. Then I'll go to the next slide. Now it is filled, yeah, now eruption. Now filled in, then matter is erupted. So this is the way matter is accumulated, ejected. Matter is accumulated, ejected, cyclic fashion. So here immediately, sad news, efficiency goes down. Because matter could not be accumulated like 2D, and as a result, all the way matter, all direction matter is able to fall to the black hole, and efficiency goes down. So 20 solar mass black hole you will not do as opposed to my previous case. But if I go to 100 solar mass black hole, it can explain ULX in hard state. This is the maximum efficiency, which is slightly below the ULX band. But again, radiation physics is not included. So although it is 3D, but not yet completely fully developed simulation. So I'll summarize in last 30 seconds. So basically, I had been targeting to understand unusually highly powerful astrophysical events, primarily jet, and some related system, ultra-luminous X-ray sources. Similar to supermassive black holes, GR seems indispensable. Black hole and its presence at the center of accretion disk in GR framework is a very, very powerful energy reservoir. Question remains, we knew this, but question remains how to tap the energy. It looked like that energy extraction is possible by magnetic field. So it is magnetic Penrose process. We know Penrose process, but magnetic Penrose process. In other language, Blandford's-Naik mechanism. And numerical simulation of accretion disk plasma in GR confirms one of the regimes of magnetic Penrose process called Blandford's-Naik effect is really not only giving fantastic theoretical prediction or numerical prediction, explaining observation. Many observations seem to be requiring strong magnetic field or predicting magnetic field's presence. So, so I targeted explicitly ULX, ultraluminous source in hard state. Though 3D gives lower power than 2D, but our system is inaccurate. Radiation physics wasn't included. So maybe in next BRIC, I'll be done. This what is GA, GCAC or whatever. Next series, maybe I'll be ready with radiation physics, and in 3D also I'll be showing most accurate and self-consistent result to explain the observation with GRMSD simulation. So bottom line is GR advection, or the advection, GR advection and magnetic field, all three quantities are required to explain observation. Thank you very much.
So maybe just a quick technical question that when you take the inside ergosphere, when the lines are twisting, so you write the magnetic field, etc., all the TMU in the ZAMO frame or the general outside observation?
Generally not ZAMO frame. But for Zamoframe also one can write altogether different story. We get through Zamoframe we are able to explicitly show the difference between Blandford's-Naik and Blandford-Payne. Blandford-Payne is not necessarily GR effect, but Blandford's-Naik is necessarily GR effect. If I go to Zamoframe, that distinction is possible. But here, whatever I had done the calculation, not in the Zamoframe.
So the simulation also, the general
Yes,
one.
simulation is done in partial coordinate to avoid all the singularity, etc., etc. So result is frame independent. Eventually, you are
sure.
extracting energy.
Yeah. Okay. Thank you, sir.
So the mechanisms you discussed, so can you, based upon this, can you distinguish between whether the progenitor is a black hole or neutron star or any other sort of star?
Yes. First of all, if it is a black hole, all those ergosphere, etc., will be there. For neutron stars, because it has extended surface, there's a high chance that those will be inside the surface. So matter could not reach as close as to the event horizon as the case for black hole. So neutron star, that is ruled out. So energy in the first place has a chance to be reduced. Though, because hard surface matter is falling onto this, so again some shock forms and extra heat can be generated. So by looking at the heat generation and energy extraction, which are related but quite independent mechanism, one can tell there is a neutron star or black hole. Also spectrally one can show for neutron star you have a two spectrum. One is accretion disk spectrum, another is neutron star surface spectrum.
I see. Okay. And one more thing is that these mechanisms can be observed for stars, like not neutron stars or gravastar.
See again, it is related to the previous point that first of all normal star, huge radius, no GR. Because everything is surrounding region, outside region.
Yes.
Normal star has no GR effect. For neutron star, effect is possible, some lens threading effect is there, but not this powerful jet effect, because I would believe that it will be halted, it will be stopped further away. Gravastar may be smaller in size.
Yes.
So tell me typically how small compared to neutron star, gravastar?
I think similar mass will be, I think it has like higher magnetic field.
Yeah, by the way, here when I talk about magnetic field, everything is a disk magnetic field, not black hole magnetic field. So again, it depends on the size. Gravastar size, I don't know much. Maybe Devoshmita may know. I don't know. She works on Gravastar. He sees here. I don't know. Yeah, what is the size? You don't know? Gravastar size. Anyway.
More questions?
Thank you.
Assume a singularity-free black hole.
Sorry?
Singularity-free black hole.
Similarity-free black
Free black hole. What happened about the magnetic field and entropy at that region where we cut the singularity?
You mean singularity?
Yes.
You mean coordinate singularity or space-time singularity?
Black hole singularity.
By black hole singularity, generally we believe space-time singularity, which is much inside the even ISCO. My all calculations are at most up to the ISCO, so that doesn't come in the picture. What you are saying, perhaps the way you are saying entropy, etc. calculation, further one has to look at the system as open quantum system, and you have to consider interaction and the basically field theory in curved space-time, which is also dissipating like Dirac equation. If suppose you consider the spinner is moving in the black hole, which is eventually giving entropy, von Neumann entropy, for example. I don't know whether you have entangled entropy in mind. So one has to look at solution of Dirac equation, which has itself dissipative term. But further you have to go, if you are talking about singularity, coordinate singularity, still one question. But if it is black hole singularity, which is space-time singularity, we never reach there.
Okay, thank you.
I would like to ask my question.
Well, technical question. Which metric you use in your calculations?
Basically, we consider curve metric, but in the partial coordinate to avoid space-time singularity.
Okay, but if you consider the black hole with magnetic field, probably you should consider not Kerr metric?
Yeah, it's a very common question. Thank you for
But,
this question. One can compute the magnetic energy density, although it is million Gauss, but if you compute energy density, it will turn out say b square by 8 pi c square. It will turn out to be very small. So basically your concern is whether it will affect the metric or not, this strong magnetic field. Though for our regular purpose it is strong, but for if I compare this with T mu nu, matter T mu nu, even actually matter also very small. Accretion disk density also you can have additional question. Accretion disk also the density. That is also very small. So those effects on the right hand side in Einstein equation is too negligible. Effectively metric does not get affected. For neutron star, which is not the case of course, but here even 10 to the power 6 Gauss is giving very small energy density.
Okay, and second comments. As I know, I'm not astrophysicist, but as I know, accretion disk is very far, situated very far from horizon. Very far, no, because there is a
It is not.
empty space, and accretion disk is far from horizon.
No.
So
Accretion is needed very small.
no, it's not bad for this mechanism, but anyway, as I know, accretion disk not in your simulation, but real astrophysical disks are far from horizon.
I am saying accretion disk generally in astrophysical system, whether you consider X-ray binary or AGN, accretion disk goes all the way up to ISCO. If it is thermal disk, it terminates by definition by Sakura and Suniev, it terminates exactly at ISCO. And if you consider advective disk system is producing hard X-ray, it terminates up to say goes up to 30 or 40 Schwarzschild. Like Ramesh, my ex-mentor, Ramesh Naran's EDAF, if you remember, if you know familiar with this kind of terminology. So if I look at EDAF, it varies depending on the angular momentum, viscosity. It could be up to 50 Schwarzschild radius. But this region, which is thermal disk, it is all the way up to ISCO. Newtonian or Novikov-Thorne. If you think Novikov-Thorne, which is a GR version of Sakura-Suniev, ISCO by definition. And people do see the spectrum I was talking about. You could explain this spectrum if you consider the emission is coming from the near horizon region, not near horizon, near ISCO region. Then only we are able to explain this spectrum. And there's the evidence, and people, by the spectrum, people are predicting black hole spin, something called continuum fitting mechanism. There are many mechanisms. Harvard group, Ramesh and his collaborator is basically looking at continuum fitting spectrum, which is based on actually this kind of spectrum, which is assumed to be coming from the near ISCO region. And ISCO is depending on the black hole spin. That way, by modeling spectrum, they extract the spin of the black hole. Okay. Maybe you are talking about super galactic, that all halo and the kind of parsec scale disk in galaxy. Maybe you can talk.
Okay, thank you. So let's thank the speaker again. And our afternoon session at last finished. And tea break. Yeah.
So we will have a very short tea break outside, and we will resume with parallel session 1. The theme is broadly early universe cosmology, which will happen here. The other parallel session will be in room number 106. Please follow the volunteers and CCSP members with red tag.